The very last one that we need to go through is actually osmotic pressure. Here, I'm going to tell you the process, okay? So if you have a U-shaped tube, and then between this tube, you put a semi-permeable membrane. The membrane only allows your solvent to pass, but doesn't allow your solute to pass. In the beginning, they have the same height. But as time goes by, what's going to happen is that the water molecule is going to go to the side that have more solute, because the nature always trying to make things balanced. If you have too high concentration, the water is going to go there to dilute that concentration. So what happens in the end is actually you'll see this goes down, that goes up. So water level will change in the end. And the height difference between the two is so-called the osmotic pressure. So here you can see that since the water trying to go to the side to dilute the solute concentration so that the concentration between two ends is minimized. So you know if you add in more solute, the height difference between two ends will become larger and larger. And the equation you want to use is actually this. Pi equals to m times r times t, where pi is the osmotic pressure, n is the concentration term, but this n is the molarity, which is number of mole per liter of solution. Okay, number of mole of solute per liter of solution. Again, it has to be this unit. If you use other concentration unit, you got the wrong number. R, in this case, is actually the gas constant. It's very important that you use the correct R, otherwise you will never actually get the correct answer. The R is 0.08206, and you have the unit of liter ATM, temperature in Kelvin, and mole. Many of students use the 8.314, which has the unit of joule per mole. This is actually not the K, not the R you want to use. So make sure you know what constant to use. Temperature has to be in Kelvin. The pressure has to be in ATM. That's all you need to know for this calculation. So let's look at one example. A solution contains 35 gram hemoglobin dissolved in water. From 1 liter solution exert an osmotic pressure of 10 torr at 25 degrees C. Find out the molar mass of the hemoglobin. Question-wise, looks very complicated, right? But what's the keyword? Yes. So once you see this keyword, what equation should you use? There's actually only one equation, right? Pi equals to mRT. T, what's T? Temperature, right? In Kelvin. So it should be 298, right? R, what's R? A constant, right? Make sure you use the correct constant. It's actually 0.08206. Pi is what? Osmotic pressure, right? Do you have the information here? What's the unit of your pi? ATM, right? What's the unit in your question? Torr. Do you know how to convert torr to ATM? Okay, 1 ATM is equal to 760 torr, right? So you know your pi is what? 10 divided by 760, right? So this will make it become ATM. Okay, so now what is the molarity? We know it's actually number of mole per liter, right? So we know it's 1 liter, so you know number of mole per liter, liter just equals to 1, right? And the number of moles defined as the mass of your solute divided by the molecular weight, right? What's the mass you have here? 35, right? And then you want to know the molecular weight. Can you actually solve this equation and get your molecular weight? I hope the answer will be yes. Okay, so it's very easy to solve this type of question, right? What's the key? The key is that you need to see the keyword. The keyword is osmotic pressure. Once you know the osmotic pressure, you need to know the equation to use. You need to know what is the proper term to use, what's the unit, right? Once you know the things, just plug it in. Then you can actually solve that the molecular weight is equals to all right. Okay, so let's talk about the application or what are the things that actually associate with it. So the first one is actually osmotic pressure actually play an important role in the medical solutions. Okay, so before I jump into this, the idea you should know is actually if today you have a membrane, okay, that's actually semi-permeable, that only allow your solvent to go through, but doesn't allow your solute to go through. If that is the situation you have, then the osmotic pressure is going to be generated. One thing you can see is actually inside our blood, okay, this is actually a red blood cell. If everything's normal, okay, we call it as an isotonic situation. So in this case, basically, the concentration inside and outside your red blood cell is more or less the same. The water just go freely in and out of your cell, and then the cell looks normally. So we call this situation as isotonic. But if today you put your red blood cell into a solution that has very high salt concentration, okay, so high salt concentration. So right now you have more salts in your environment than inside the cell. The reason that you see the osmotic pressure is because the water will always go to a direction that is going to make the inside and outside concentration become similar. Outside the cell right now you have so high concentration of salt. Therefore, the water inside your cell want to go out. And in that case, you will see the cell start to shrink. So under this case, we call it as hypertonic situation. In the opposite, okay, if you just put your cells into a solution that only contains your water. So right now it's actually inside your cell, you have a very high salt concentration, right? Outside is just water. So the water from the outside will try to get into your cell. It will actually make your cell start to swell, eventually break the cell. Okay, and for that case, it's so-called the hypotonic situation. So that's actually a simple concept that associated with the osmotic pressure. So the other interesting one, so there are actually a couple, I will just pick two for today's lecture. The other thing that you will see this application very often is actually at home. Many of you must have this reverse osmosis water filtering system, right? And then what it does is actually, typically you will see the filter, and then you're going to see a water tank. If you have this, but you never actually look at it, go back home and look at it. So what's going to happen is actually, that is actually the tap water coming out from your faucet, okay? So you put the tap water goes into your filters. Some of the water will go to these sides, okay? But because there are many salt on the right-hand side, right? So at a certain point, the water won't go to the left-hand side anymore. So you're going to see these things start to form the osmotic pressure. So what your filter do is actually they're going to exert certain pressure, push the things to the left-hand side. And these things will actually eventually go to the tank and get stored. And then you're going to see many tubes, okay? And then one tube is actually, because the force it exerts from your setup is actually a constant. Okay, that means actually they can only push certain amount of water to the left-hand side. So what they do is actually there'll be actually a tube that fit in the tap water constantly and bring out this water, the salty water out too. So they can make this process continuous. So let's actually the applications of osmotic pressures. Okay, so these Van Hoff factors will actually play important roles in your homework. To know how to actually estimate these Van Hoff factors correctly, so you can actually get the calculation done properly. The Van Hoff factor is basically equivalent to the concept that you learned previously. Okay, when you calculate the normality, we introduce a concept called the number of equivalent. For the non-electrolyte, your Van Hoff factor, which always written as I, the I is always equals to 1. Okay, but for the electrolyte, okay, it changes. So right now the thing is actually what is non-electrolyte, what is electrolyte? So what is electrolyte? Whatever substance that can actually generate ions in your solution when they dissolve, those things are called the electrolyte. If it cannot, then it's non-electrolyte. So the commonly seen electrolyte including what? 3 things: salt, acid, base. If it's not salt, it's not acid, it's not base, then it's a non-electrolyte. Okay, so if you look at this table, it will give you a better idea. Glucose is not a salt, it's not an acid, it's not a base. Okay, it's just a molecule. And once it dissolves in waters, okay, it did not generate ionic species. So we call the glucose as non-electrolyte. So if it is non-electrolyte, then its Van Hoff factors is going to equal to 1. Okay, then we can actually start to talk about the electrolyte now. So all the things I highlight here, they are actually all electrolytes. What is HCl? Acid, right? Is acid an electrolyte? Yes, right? So once it dissolves in water, it's going to become H plus and Cl minus, right? So even though you just dissolve one HCl, you produce 2 charged species. So that 2 is so-called a Van Hoff factor. Another example, NaCl. What is NaCl? Salt, right? It's salt electrolyte. Yes, okay, so what will it become once it dissolves? Na plus plus Cl minus, right? Okay, so how many charged species if one NaCl dissolve can generate? 2. So the Van Hoff factors for your NaCl aqueous solution is 2. I found students actually got confused about these things. MgCl2, it is actually also a salt. So once it dissolves, what are you going to get? Mg, what's the charge? 2 plus, good, and then plus Cl minus and 2. How many charge species you have generated? 3, right? So the Van Hoff factor is 3. I will leave the remaining for you to practice. Okay, but the key thing is what? Key thing is actually, can you recognize the acid, base, and salt? If you can, that's the first step, right? You know it's actually electrolyte. Van Hoff factors cannot be 1. Then what is the Van Hoff factors? Then you can actually write out the dissociation equations. So you will know how many charged species will be generated. Once you have these Van Hoff factors, why does it matter? Okay, it actually matters regarding to actually associate with your collective property, right? Because when we talk about the collective properties, actually it only matters about number of molecules, okay, or number of particles inside your solutions, right? So because it is electrolyte, okay, even if you're just doing 1, effectively you actually produce 2 molecules in the end, right? So you need to actually correct for that. So in all the equations that you have, like delta TB, delta TF, or the osmotic pressure, you need to actually add in the Van Hoff factors in the front, so they can actually calculate the proper collective properties. So that's the reason why we need to introduce these Van Hoff factors right now. We are going to go through 1 examples. Okay, so find out the boiling point of 0.9 N FeCl aqueous solution. Boiling point is actually a keyword that you need to recognize, because once you see the boiling point, you know it has to be the collective property. So when you read the questions, the question can be actually super long, right? You need to know what equation you want to use. Okay, in this chapter, that's only a few keywords that you need to memorize, right? Vapor pressure, freezing point, boiling point, osmotic pressure. Because all these four is going to tell you to use the collective property equations. Okay, so you can quickly locate what are the equations that you need to use. So for the boiling point, this will be the go-to equations, right? Delta TB equals to I times K times N. And then, of course, there's another one you need to know is actually the boiling point of your solution is going to equal to the boiling point of your solvent. Plus or minus your delta TB? Plus, right? Plus your delta TB. So you know this equation that's going to give you the correct answer. How do you calculate these two terms? What's the boiling point of your solvent? So what is your solvent? So how do you know it's water? Aqueous, so it's water. Boiling point of water? 100 degrees C, right? Okay, 100 degrees C. How do you calculate your delta TB? We know it's actually I times your Kb times your concentration of your solute, right? What is I? So your I for your FeCl3. FeCl3 is electrolyte or non-electrolyte? Electrolyte, right? So once it dissolves, FeCl3 is going to become Fe3 plus, right? Plus 3Cl minus, right? Therefore, I equals to 4. How about your K? Kb. What is that Kb? Who's Kb you should actually looking for? Water, right? So if you go to your textbook, okay, you can find the Kb. So you'll find that Kb is equals to 0.52. When you do your homework, it will be provided. Then you need to calculate the concentration of your solute. What's the concentration of your solute? 0.9, right? Okay, then you do these calculations. Then you will find out the final answer is 101.872 degrees C. So it is less simple. What is the key thing? The key thing is actually you need to actually looking for the equation first. You need to know what is your solvent, what is your solute, so that you will know what is the boiling point of your solvent. And then you need to actually make the judgment on what the solute you have is actually electrolyte or non-electrolyte. So you can determine your Van Hoff factors. And you need to know where to looking for the proper Kb for your solvent. Then you need to know what is the concentration of solute you should use. Once you have all those information, you can solve these things without any problem. Then we can actually start to talk about some really interesting thing. I think that's pretty much the very last page of chapter 10. Okay, so you can see like scientists, they just keep pushing the things smaller and smaller. Nanometer is actually the things that become very popular about 20 years ago. Now it's still very popular. You can see many research labs at UH. The main thing they do is actually want to prepare particles in the nanometer size region. They realize that if I make a particle less small, if I throw it into solutions, they did not actually dissolve. But even though they did not dissolve, it looks transparent. The way they figure out it doesn't dissolve is simply because if today I add in some of these nanoparticles inside my solution, they form these homogeneous solutions. But if I just let it sit on the table for half hours, then they start to see precipitates at the bottom of the container. So what this means is actually it doesn't really dissolve from a homogeneous solution, right? Because if you form a homogeneous solution, even you put a layer for half hour, it won't precipitate out. You will still see a homogeneous solution. That's the very beginning. People realize, okay, once I make a molecule so small, okay, it can actually suspend inside the solution and make it look like a solution, even though it is not. And then they actually bring in many interesting phenomena. One thing that's very famous regarding to this is actually the scattering. Since we're going to talk about scattering, the first thing to talk about is actually light. Okay, so why the colloidal solution is so cool is because they realize, okay, if today you make the size of the particle so small, that only contains tens of nanometers. Okay, that's the size we're talking about. It's actually smaller than the wavelength of your light. So what's going to happen is that I'm small, okay? And then when the light hits me, I can only reflect the wavelength that's closer to my size. In the sky, you have many gas molecules, right? Okay, and those gas molecules at high altitude, the temperature is actually low. They're going to start to form some small aggregates. And the aggregates they are going to form is actually in the nanometer region. What happens is actually those aggregates, they can only reflect a shorter wavelength of light. We just mentioned that the eye can only see for very limited type of light. So if you have a small particles in the air, it's going to scatter the light that has wavelengths that closer to its size. They can only scatter the blue light. Once they scatter blue light, it's just blue light and eventually go to your eye. You can see why the sky is blue. So then let's talk about why these things is so cool. If today you prepare these nanoparticles and then you suspend it in the solution. So if you don't shine light on it, it actually looks transparent. But if you shine light on it, it's going to scatter the light. Okay, so here you can see there are two solutions. Okay, so this is a solution with nanoparticles. Okay, and this is actually just a glucose solution. So we know glucose can actually dissolve in water perfectly, right? So once it dissolves, it's actually a single atom or single molecule dissolved with your waters. It's actually a homogeneous mixture. Okay, you don't have a particle layer. Glucose just a couple of carbon bonds. So the size of light is so small that it did not scatter the light, so the light just passed through. That's why you see, even if you shine the light on the glucose solution, you don't see anything. But if you shine the things on a solution that suspend your nanoparticles, those nanoparticles are going to scatter the light. And the light is scattered is going to depending on the size of your nanoparticles. So that means actually if you change the size of nanoparticles, the light you see here, the color will actually change accordingly. So this is actually a particle that's actually larger in size that can scatter more this kind of light. So it's not scatter the blue light, right? Because the size is actually now bigger. It's going to scatter a slightly longer wavelength light. All right, so all these phenomena, okay, is so-called the Tyndall effects. Basically, it's just small particles that can scatter the light. That's why the colloidal solution become very popular. Okay, and another thing is because when people design these nanoparticles, they found, okay, if I create a heterogeneous catalyst, the things people always want to do is actually want to maximize the surface area. If you can make the heterogeneous catalyst into less small size, then you actually maximize the surface area. And then because it's actually recollectible, right? Because if you put that in the solution and then let it sit for a while, you can actually recollect all these things easily. So there are actually many applications based on this idea in chemistry. That's why the nanoparticle chemistry is actually right now one of the most popular research fields. All right, so I think I will stop here.